So the Newton-Raphson is very good compared to the fixed point iteration. I actually in 2 slides earlier for example 6.3 or in the topic that I was talking, I mentioned about bisection, but I should have said fixed point iteration because these are the open methods. Compared to the fixed point iteration method, sometimes the Newton-Raphson can give slower convergence, but this is some rare cases. Usually the curve of the function is very steep, then it can create a problem for the derivative anyway. That's why there can be some slow convergences. And we will show an example here in example 6.5, this example. And we will solve this by using Newton-Raphson by starting from x equals 0.5. So let's remember the formulation first. Xi plus 1 is equivalent to xi minus fxi divided by f prime xi, the derivative. So we know the function, but we don't know the derivative. Then let's calculate the derivative of this. 10x to the 9 minus 1 is 0, just this value. So if we plug these in here, then we will have xi plus 1 is equivalent to xi minus xi to the power 10 minus 1 divided by xi 9, 10 times xi 9. So we will use this to calculate things. So here you should see we start with x equals 0.5. You should be careful here for choosing this, because if you choose, for example, 0 or very close to 0, you will get 0 here, and this will take this division to infinity, and you will not get a solution. So be careful not to choose a value which makes this 0 with the denominator. The term under the ratio shouldn't be 0. Make sure of it. So we start with 0.5 here. So let's say I equals 0, then x 0 is 0.5. Then our formulation is x1 x0 minus x0 to the 10 minus 1 divided by 10 x0 to the 9, like this. So here for x0 we will put 0.5, then x1 is 0.5 minus 0.5 to the 10 minus 1 divided by 10 times 0.5 to the 9, and the result is 51.65. You can see it increased like crazy. So and from the equation actually you can simply see that if we equate this to 0, then x true should be 1, and you see that our value is now 51, and from 0.5, which is very close to the root, we moved to the 51.6, so it jumped like crazy. But after a while it will actually get slower and will converge to 1 eventually. Let me show a the first iteration. I equals 1, x1 is now 51.65, then x2 is equivalent to 51.65 minus 51.65 divided by 10 to the power 10 times, sorry, here to the power 10 minus 1 here 10 times 51.65 to the power 9, and here x2 is 46.485. So it started to reduce, you can see, but not much. So I will continue, but I will not calculate the rest. You can make it, and you can see the results here. It goes up to 51, then goes down to 46, 41, 37, 33, and eventually it will go to 1, but it will take forever. You can see it goes like to the infinity, and this means we have a slow convergence to the root. So that's the biggest issue that we have with Newton-Raphson, and the reason is the curve is actually very steep. Maybe here we can draw the curve. If x equals 0, then fx is 1, minus 1. For 0 it's starting with minus 1. So from here it goes like maybe too steep like this, and we chose this 0.5, and the derivative maybe took us somewhere up here. Then here actually x is 51. So we continue trying to find the root, but it doesn't able to go. It goes slowly over here, goes coming, and eventually it's coming here. So we will see as a slow convergence, and these issues are important to interpret by simply drawing the curve of the function first. You can just draw this, see the curve. If it has something steep like this, then you should be careful on using Newton-Raphson. So maybe fixed point can be better, or you can find another alternatives to solve this issue, and we will show those after talking about this slow convergence issue furthermore in the following slides. In this slide, we will see further about the issues with Newton-Raphson method, and they are basically based on the derivative, because the derivative is a denominator in the formulation. Let me write it down here again. F(xi) divided by f derivative xi, and it was xi minus, and this is xi plus 1. So this denominator is important. And the near zero derivatives are big problems. And in the first issue, for example, an inflection point, that is, if derivative is 0, may occur in the vicinity of the root. So let's see the root first. The root is here. And here, these are very close to the roots, but still, maybe here as well. The derivative is very horizontal almost. And that means this is very small, close to 0. Which makes the predictions diverge from the root. So we started here from x0, it came here, and in here the function value is this. And from here the derivative takes us to here, x2, and x2 takes us as the derivative further far away from the root, so it diverges. So we shouldn't make this close to 0. The second issue is similar, and we have again, so the root is here, but we started from here, for instance, and the derivative is again maybe very small, or it's like over here going to the other way. Then x2 is taking us here, then x1 is taking us to x2, then x2 is taking us to x3, and x3 is taking us to x4, and it comes here somewhere and converging here as if it is a 0 value. But it doesn't work fine here because maybe it's very far away from the root, and there is again near 0 slope. So near 0 slope is dangerous. And here again it is diverging. That's a big problem. So to eliminate these issues, maybe we can start from a different point. Just change this. If it is diverging, start from here, for instance. Here as well, start from somewhere else, closer. Closer is better here because when we get farther away, it's like much nearer to 0, the derivative. The issue 3 is that we can have one root, so we can have an initial guess that is close to the one root, and it can jump to a location several roots away. So here, for instance, we have this root and this root, but we started from here, and the derivative here actually made us jump here instead of like closing to here. It jumped here, then from here it jumped to the other root, like over here. The other root is here. This is again about the 0 slopes, and at the top especially you can see that the slope is horizontal, here horizontal, maybe you cannot even reach there. And this is the fourth issue. If f derivative is directly 0, that's a truly disaster, because it results in division by 0 in the Newton-Raphson here, as I said earlier, and the solution shoots off horizontally and never hits the x-axis. So here, for instance, x0 is here, coming here, And here suddenly it's like parallel to x-axis, the tangent, which means this is 0, and it goes to infinity, and you cannot even find any solution over here. So you have to be careful about these issues. If the root is diverging, actually going away, or the derivative is very small, then you can think that maybe I shouldn't use this Newton-Raphson because the derivative is too small, and change my numerical method. Or you can start from another initial guess which doesn't have a derivative near 0. It should be farther away from 0. This is the algorithm for Newton-Raphson method, and basically this is very similar to fixed point iteration. The only difference is that we have now the Newton-Raphson method formulation, and in here we have the derivative as the denominator. That's why we need a function for the derivative as well. So we added this as the first modification, and first derivative should be computed using a user-defined function. So initially maybe you can just type the derivative over here somewhere, or that should be coming from outside to the function. So that, or this can be a function by itself, and you should define that too. And this program should also be improved by incorporating several additional features to solve the potential issues that we mentioned in the previous slides. So the final root estimate, so let's start with the first. A plotting routine should be included in the program so that in the plot you can see the derivatives if they are parallel to x-axis or if they are closer to 0, and if it is diverging or not. You can simply see them. And the final root estimate should always be substituted into the original function. So just when you find an XR, just substitute it to the function because we have the function. And our estimation is that we have the function, but we are not able to find the root. That's why we are using this numerical approximation methods, Newton-Raphson. So we have the function. Just plug the value in, this XR value. Then if it is closer to 0, then that's good, that we are actually getting closer to the value. So this check partially guards against slow or oscillating conversions, which may lead to a small value of the approximation error, while the solution is still far from the root. Another modification can be that an upper iteration number limit is required to guard against oscillating, slowly convergent or divergent solutions. So here also you can see this is the maximum iteration number and this is the iteration number. So we can just set, for example, 100 iteration maximum. After that it stops. So either the error threshold stops it, or the iteration number. If it is larger than the maximum iteration number we set, we stop. The program should alert the user and take account of the possibility that f derivative might equal to 0 at any iteration. So if the derivative here, we can add an if statement. If the derivative is near 0, we can set a threshold maybe, then stop. It can give a warning that change the initial value because the derivative is near 0. And the fifth, the trial with various initial points can also be considered. We can randomly generate different numbers to start with different values to eliminate the divergence issue, and we can compare the results for each of these. So we can simply multiple times we can run this, compare the results, which one gives the best error and the lowest error. Let's say it is a possible initial guess that we need to start and solve the problem. So these are some solutions that we should use, not only for Newton-Raphson, but also for the following methods that we will show.